Audible and visible. Could you please confirm that I'm still audible?
You are audible as well as visible.
Okay. So, good evening, everyone. I hope everyone is doing well and staying curious. On behalf of the Eka Research, I would like to warmly welcome all the participants joining us today for this special webinar session. My name is Unisa Botta, and I'm your host for today, as well as co-member at Eka Research. Before we officially begin, I want to share something small yet quite personal. Growing up, science was always what something that fascinated me, but not only in formulas or theories, but because of the questions behind them. Questions like why does the universe work the way it does? And how do scientists even discover these things? Well, honestly speaking, the more answers I found, the more questions I had. And I think that curiosity is exactly what brings all of us here today. I believe one of the most beautiful things about science is that it both humbles and excites us at the same time. That sense of curiosity is always one of the reasons I was genuinely excited to begin my journey at Eka Research. For those joining us for the first time, Eka Research is an interdisciplinary nonprofit organization dedicated to advancing research, scientific learning, innovation, and outreach in STEM fields. Since 2020, we have been actively engaging communities through workshops, webinars, research discussions, training programs, and astronomical observations. Our goal is to make scientific learning more accessible, engaging, and community driven. Today's webinar will explore rare gases using coincidences spectroscopy, which is focusing on how this technique helps us study ionization processes, electron dynamics, and atomic interactions in noble gases. And I believe many science enthusiasts like me are excited to hear more about it. Now, coming to today's session, we are truly honored to have with us Mr. Sunny Labh. Sunny Labh is a physics researcher, science writer, and science communicator currently pursuing his master's degree at the University of Kassel in Germany. His current thesis work focuses on Auger decay in rare gases using coincidence spectroscopy at advanced area of experimental and atomic physics. Alongside his academic research, he is also widely recognized for his remarkable contribution to science communication through his writing on Medium app, where he has built a community of more than 29K followers. He explores topics ranging from quantum mechanics and mathematics to the history and philosophy of science. His articles reflect not only deep scientific interest but also a genuine passion for curiosity, learning, and scientific culture. I will be providing the links in the chat section and urge the participant to check them out. So, without further ado, it is my absolute pleasure to hand over the session to Mr. Sunny Labh. Welcome, sir, and thank you for joining us today.
Thank you very much for so kind introduction. I hope I'm properly audible.
Yes, you are.
Okay. First of all, thank you very much for inviting me, Eka Research, and it's really an honor to be here and be able to speak about my research today. I think you guys are doing a great job. I'll very quickly share my screen. Can you see the screen? Yeah.
Yeah, it is
Yes.
visible.
Okay, so let's start then. So today's topic is, as Eunice already said, it's about Auger decay in rare gases or in general any atomic or molecular systems using a technique called coincidence spectroscopy. And this is also my field of research at the moment. And for those of you who don't know, I am a master's student at the University of Kassel in Germany, and I'm currently in the Erasmus group, which works primarily with synchrotron radiation physics. And spectroscopy. So the diagram that you are looking at right now on the screen basically is an energy level diagram. We will talk about this in a bit more detail very shortly. But first, let's try and understand why do we need to study rare gases? Why study rare gases at all? So the first point is that noble gases or rare gases like krypton and xenon provide very clean, isolated atomic spectra, which make them an ideal test systems, meaning that if we have a very complex molecular or atomic systems which are highly reactive, it's quite difficult to work with them. Whereas noble gases or rare gases are pretty stable naturally, and they provide very clean spectrum. And so it's quite easy to work with and analyze, basically. Second is they are used to benchmark electron correlation models and study Auger cascade dynamics. I will explain what Auger decay basically is quite extensively very shortly. But to say in simple terms, they basically allow us to see how electrons correlate with one another and how atoms excite and de-excite in a certain system. And thirdly, Auger emitting isotopes, for example, are also explored for targeted cancer therapy and radiation damage, while rare gases like xenon serve as a model system for understanding these processes. So what happens is that there are radioactive isotopes like iodide, which are involved in radiation cancer therapy, wherein slow electrons are used to target cancer cells and destroy them, basically. And they work quite well because slow electrons specifically, are very important particles or something that can be locally used to target cancer cells, and it is quite extensively used. And rare gases like xenon basically help us understand how that process basically works, because xenon is quite close in atomic configuration with iodine. So this is another practical application of why it's important to study rare gases. The diagrams that you're looking in your screens right now basically is, the first one is the coincidence map. This one is something called coincidence map, and we will learn about that, how to build one and how to interpret these maps. This is an image that was taken while performing the experiment, and this is a sample atomic spectra. Before moving forward, let me very briefly tell you what coincidence spectroscopy basically means. But before that, what coincidence basically means. So we all know, I think, what coincidence means. It means that when two events are happening at the same time, or two incidents take place at the same time, it's pretty much the same in atomic systems as well, wherein two or more electrons or two or more ions are detected at the same time from the same ionization event. Ionization basically means that you are, for example, you ionize an atomic system when you hit that system or that atom with an external photon or light energy or any other form of energy, basically. That's what ionization is. And coincidence spectroscopy is a very powerful tool to study these systems. So in this context, coincidence is the simultaneous detection of multiple particles from the same ionization event. And it provides correlated information on electron and ion dynamics, basically how electrons and ions work and how they are correlated with one another. And it also enables reconstruction of complex decay pathways. And by decay pathway, I mean when an atom or molecule is excited, it also needs to de-excite by certain phenomena, by certain processes. And Auger process is one of those processes. And it is also a powerful tool for studying many body interactions and ultra-fast processes. But this method or this technique cannot be done so easily, and it has certain conditions that are needed in order to basically detect electrons in coincidence with one another and to excite atoms or molecules in that level. And the first and a very important condition is that the radiation source or the source that is used to excite the atom or the molecular system should be a pulsed source so that we can basically distinguish or differentiate the ionization events. And this is only possible, at least so far, with the help of synchrotrons or free electron lasers. FEL basically stands for free electron laser. And synchrotron, I will talk about synchrotrons in a little while. It's basically the release of X-rays by accelerating electrons close to the speed of light. And another very important condition is that there need to be ultra high vacuum, which means that we need to reduce the pressure to a considerable amount, close to 10 to the negative 5 millibar or less than that, in order to be able to have proper excitation and de-excitation of the system. And vacuum condition is also necessary so as to not have any external contamination in the interaction chamber. And third very important point or condition is that there need to be a controlled target density and beam intensity to suppress random coincidences. And by random coincidence, I mean that because the radiation is bunched or pulsed into multiple sections or segments, there can be other coincidence events or other electrons that could be detected in a different detection time frame, for example. So that needs to be considered and taken care of quite properly while performing the experiment. And fourth is that it requires a simultaneous measurement of multiple fast and slow electrons with good energy resolution. Now, what it means is that the detectors that are used to, for example, detect these electrons have to be very sensitive. They have to be properly tuned to detect these kind of electron dynamics and processes. And so because these kind of experimental conditions are not so easy, so this experiment cannot be conducted everywhere. So we need synchrotron radiation facilities or free electron laser facilities to be able to pull off this kind of experimental condition. The photograph that you're looking at your screens right now is Petra 3, which is a synchrotron radiation facility at DAISY in Hamburg. DAISY stands for Deutsches Elektron Synchrotron. And basically, as I said earlier, synchrotrons are the particle accelerators, basically, where electrons are accelerated close to the speed of light. And those accelerated electrons radiate extremely powerful X radiation or X-rays. And those X-rays are carried out to multiple experimental stations to do further analysis and so on. And the data that I'm currently working on, for example, for my master's thesis, was taken at Petra 3, at DAISY, at this very facility that you're looking at. Maybe it'll be a bit more clear about how synchrotron radiations work. I have a very short video from YouTube. Maybe that will help understand what synchrotrons are and how they really work. Wait, can everyone hear the sound and see the video? Or I hope it's, sorry. Just a moment. Oops. Why isn't it working? Okay, hang on a minute. Yeah.
An electron gun fires bunches of electrons through steel tubes into the booster ring. Microwave energy is then used to accelerate the electrons up to nearly the speed of light. The electron beam is then injected into the synchrotron storage ring. When the path of these high-speed, high-energy electrons is bent by magnets inside the storage ring, a natural phenomenon occurs to produce an extremely brilliant light. Beam lines capture, manipulate, and direct this light onto samples. The interaction of light with molecules in the samples allows scientists to obtain very detailed images of the molecular structure of materials, as well as a very detailed chemical analysis.
Okay, so basically, as you saw, what happens at the most fundamental level is that a beam of electrons is released, and those electrons are accelerated close to the speed of light. And because of that acceleration, there's a systematic arrangement of magnets, which are called undulators, which are basically in those closed rings. And when the electron passes through those rings, those undulators, they basically emit X radiation or X-rays. And those X-rays vary from energy close to, say, 10 electron volts or 2000 or 3000 electron volts, basically in the regime of both soft and hard X-rays. And those X-rays can be used again to basically analyze atomic and molecular systems, or even with biological systems, they are quite extensively used and very useful. But synchrotrons are just one example of particle accelerators. We can also use, we can also use something called free electron lasers or X-ray free electron lasers. The images that you're looking at right now is again from Hamburg. The upper one basically shows a linear accelerator, and it is fundamentally similar to the principles of how a synchrotron radiation works. But it is different in a sense that it is linear. As you can see, it is quite straight and not round. And the way it works is that electrons are released. They are accelerated again close to the speed of light, and they travel quite some distance through those undulators or magnets or magnetic arrangements. And they accelerate close to the speed of light, and because of that, they produce X-rays. And those produced X-rays again interact with the electrons, which are again on the way. So this process happens at the same time, simultaneously. Those X-rays interact with the electrons to form bunches, or micro bunches, as they call it. And those are extremely, they're basically pulsed. And it's like singing. If 10 people are singing a chorus at the same time, the energy is quite intense, right? So it's basically similar. If multiple, let's say, bunches are produced at the same time or are pulsed together, then they are quite intense. And X-FELs or X-ray free electron lasers are quite powerful as compared to synchrotrons, basically, because they produce ultra short and extremely intense and bright X-ray pulses. They have very high brightness as compared to synchrotrons. The pulse duration here is typically in the range of femtoseconds, whereas in case of synchrotron radiation, it is in the range of picoseconds or something like that. And they are very ideal for studying fast or ultra fast dynamics. And by that, what I mean is that there are processes in atoms or molecules, or even in biological systems, there are certain processes which happen extremely fast. And conventionally, it's not possible to study those processes with regular experimental setups. And so these extremely sophisticated facilities have to be built for anyone to be able to see or understand or analyze those processes. And this example here, the picture above that you see is from Germany itself. It is located at Hamburg. And this is called EUXFEL, or European X-ray free electron laser. I think there are around 11 or 12 free electron lasers all over the world. and close to 60 or 61 synchrotron radiation facilities. And this lower diagram is a pictorial representation of how a synchrotron works. So here we have an electron gun. From here, the electrons get produced. A beam of electrons, as you can see, it passes through accelerator, which produces electromagnetic radiation or waves in order to accelerate these electrons. These electrons then enter something called undulators that I talked about earlier. These are basically arrangement or systematic arrangement of magnets. And because electrons pass through those undulators for quite some time, they produce X radiation, which are then used at experimental stations where we put our setup. And then depending on what you want to analyze, you then use these pulses or these radiation. Let me give you a little bit of historical background about Auger decay, or what Auger process basically is. So I think everybody here is familiar with Albert Einstein. Is there anyone who doesn't know who he is? Okay, I'm presuming everybody knows who Albert Einstein is. Very familiar, very popular all over the world, one of the most popular scientists that we know. And he basically explained an effect or a process called the photoelectric effect in 1905. Basically, the photoelectric effect explains how electrons are ejected or removed from a surface when that surface is basically incident, or when that surface is struck with photons. So what we do is we have photons or light energy, and then we strike that on a surface, and electrons are ejected. Basically, Auger decay also works on the very same principle. And the Auger process was first discovered by Lise Meitner in 1922. A lot of people don't know about her, but she's quite an important figure in nuclear fission, for example. For those of you who don't know, she is also considered as the mother of atomic bomb. Like Oppenheimer is recognized as the father of atomic bomb, she's the mother of atomic bomb. And she was also responsible for basically discovering this process, along with a guy named Pierre Auger, who independently discovered the same process in 1923. Throughout this presentation or talk, I will use the term Auger process, but keep in mind that Lise Meitner had equal contribution in discovering this phenomenon. Now, unfortunately, you would need a little bit of scientific background, or at least physics background, to be able to understand what this basically is. So what you see here is an atomic energy level diagram. These black dots that you're looking at are the electrons, and there's 2s, 2p1/2, 2p3/2, and so on. These are the atomic levels. And so Auger process basically shows, basically is a process where an electron is kicked out from one of the shells or orbitals of an atom, and that creates a hole basically in that shell, which is then filled by an electron from another shell. In this case, you can see this is 3p shell of an atom, and a third electron gets kicked out. Okay, so let me repeat myself. Auger process is a three-step process basically, wherein an electron is ejected, or a hole is created, an initial vacancy is created in the inner shell of an atom by using photon, or in this case, synchrotron radiation, as we talked about earlier. And then because of that hole, the atom is unstable. And so that hole needs to get filled up by another electron. That electron comes from another shell, and because of the energy released of that electron transfer, a third electron gets kicked out from another shell. And that's what the Auger process basically is. So it's three steps: initial hole, an electron filling that hole, and a third electron getting kicked out. So what you're looking here is a normal Auger process. In the initial state, you can see there's a single hole over here, which is created by by photoionizing this atom. And this electron comes down here, fills up the shell, and because of the energy released in this process, a third electron gets kicked out. Yeah. So I hope this is clear. And in this particular example, here you can see 2p minus 1 is the state, or is the nomenclature that we use to denote this state, this initial state over here. Minus 1 because, as you can see, generally in s orbit, in p orbital, for example, 2 electrons and 1 is missing. So we use minus 1 over here. This is short with 1 electron, so we use minus 1. And here, because there are 2 holes remaining at the end, or in the final state, we say it's 3p minus 1 for this shell and 3d minus 1 for this shell. So at the end, there are 2 shells, or 2 holes that are vacant. Similarly, this can happen also with a process where the initial hole exists, and that hole is filled up by an electron of the same shell. As you can see, both of these are same shells, 2p, 2p 1/2, and 2p 3/2. And we write 1/2 and 3/2 because of this something called spin orbit coupling. I'll not get into the details of what it is. It's basically splitting the energy level or the shell of an atom. But they are essentially the same shell. So what happens is an initial hole is created in one shell, and a second electron fills up that hole, which again belongs to the same shell, and a third electron gets kicked out from somewhere else. Yeah. So I have included the diagrams here to make it easier for you to understand. You can see there's a hole which is filled up by another electron from the same shell, and a third electron gets kicked out. So here, the involved shells are the same, and this is something called a CK transition, and it is also a type of Auger process. I'm trying to go as slow as possible from my side so that it is easier to follow. And there's a third example wherein we have a hole in this shell, for example, which is the 3p 1/2 shell, or in orbital configuration, it's called M2 or something like that. I think this is X-ray notation of shells. So you can call this M shell, which is then filled by a second electron from M shell itself, and a third electron gets kicked out from M shell, meaning that the shells or orbitals involved here are the same. Yeah. So these notations that I have used here is ionic notation. This denotes the initial and the final state of the atom, meaning that right after creating the initial state or initial photoionization, and after the completion of the Auger process. So this basically corresponds to this process wherein we have 2p minus 1 initial state, 3p minus 1, 3d minus 1 final state. Here, 2p minus 1 initial state, 2p minus 1, 3d minus 1 final state. As you can see, 2p and 2p are the same shells. Yeah. So this is second type of Auger process. And here you can see 3p minus 1 initial state, as in this initial state, and 3p minus 1, 3d minus 1 final state. So in all the cases, we have 2 electrons missing. Yeah. Here, 2 electrons missing, one from this shell, one from this shell. Here, 2 electrons missing, here, 2 electrons missing. This is what Auger process is. And they have names. Yeah. So here, as we saw, the 3 shells involved in the process are different from one another. So we call it basically normal Auger process or normal Auger decay. In the second example, I told you that the shells involved are basically 2 of the shells are the same, meaning that 2p minus 1, 2p minus 1, same shells. As you can see here, initial hole and the contributing hole is the same, is from the same shell. So this is basically something called chronic decay or CK decay, for example, and it is also a type of Auger decay. And if the involved shells are the same or involved orbitals are the same, we call it super chronic decay or super CK transition or super CK decay. Yeah. I hope this is clear to everyone. I gave a disclaimer already that if you don't have a physics background, it might be a little bit hard to follow these concepts. But nevertheless, I have tried to make it as easy as possible from my side. So if you have studied physics in your high school, I think you must have come across the photoelectric equation or photoelectric relation given by Albert Einstein. So what we have here is photon energy that we use from the synchrotron radiation. Yeah, we can tune the amount of energy that we use. And then we target the atom or atomic system, which has a specific binding energy. And then we can evaluate the kinetic energy of the released electron. The same process works also in the normal photoelectric effect. It also applies here. So we can calculate the electronic kinetic energy by using binding energies of the atom and the photon energy that we use to excite that atom. And we can also evaluate, for example, the kinetic energy of the emitted Auger electron. In this case, this electron, this electron, this electron, by using this simple equation or formula, where basically this EBI is the binding energy of the initial state. Yeah, initial core hole. In this case, this is the initial core hole. And J and K are the two levels which are involved in the decay, meaning that these two states are involved in the decay. So we use the binding energies of these states. Binding energies is basically the energy by which the electrons are bound in the atom or atomic orbital. Yeah, so that's the amount of energy that you need in order to kick that electron out of that shell. Yeah, so if your provided energy is greater than the binding energy, you will be able to eject the electron out. If it is less, you won't be able to do it. It's common sense, right? And here we have a correction factor, which comes from electron-electron interactions or basically PCI effects and so on. So fundamentally, basically, the emitted energy or the kinetic energy of the emitted electron or ejected electron depends primarily on the binding energies of the shells and not the photon energy. Okay, this is an important piece of information that you need to keep in mind. So we performed an experiment at Petra 3, P04 beamline at DESY, as I said earlier. And the photon energies that we used was 1830 EV, 1673 EV, and 1660 EV. So I'm currently working with all these photon energies. And these photon energies are basically good enough to eject an electron from the 2p shell of krypton. I'll be giving an example of krypton because that's what I'm working on right now. So the binding energy is here for 2p 1/2 is 1730.9 eV, meaning that we need an energy greater than this energy in order to eject an electron from this shell, right? And for 2p 3/2, it's 1670.4, close enough, but slightly different because of the spin orbit coupling, as I said earlier. And these are the binding energies of 3p and 3d shells. Okay, these 3p, 3d, 2p, these are the shells or different levels of an atom, orbitals of an atom, where electrons live. Yeah. So we used 1830 eV of energy, which is good enough to ionize electrons from all of these shells. Yeah, because it's greater than those energies. And for your ease, I have used two types of nomenclature here, both ionic notation and the orbital notation or X-ray notation. This L2 and L3 means 2p, right? M shell basically means 3p, 3d, and so on. And we use krypton monomers, krypton clusters, and also argon at multiple photon energies, which was basically used for calibration purpose. So monomers basically are individual atoms. Yeah, clusters are a group of atoms basically produced from the cluster source, which are because when you use an isolated atom and when you use atoms in clusters, it might give different results because the atoms are very close to one another. And because of that, the photoionization and de-excitation processes might be slightly different. And that's what I have been intending to see in my data as well. I'll talk about that shortly. And the detection system that we used was something called electron time of flight spectrometer, which in very simple terms is basically the machine or the device that detects the electron or the ejected electron. Yeah, so it is the detector that says that, okay, this is one electron that I found, this is another electron that I found, and so on. And the detection system is also capable of electron-electron and electron-photon coincidences, meaning that it is capable of identifying or detecting electrons which are coming from the same ionization event. And please don't feel overwhelmed, but this is a setup from my experiment. I will not obviously get into the details of what these components really are, but this image that you see here, this one that you see here first, is the setup at our university. So we basically prepared and assembled everything. Well, I didn't do it myself because I'm looking at the data right now. But yeah, this is basically the setup that needs to be that was assembled at the university. It was taken to the synchrotron radiation facility, and this is a photograph of the facility. So you can see it has multiple components. It has the interaction chamber. It has the point where the detector is placed. It has the section where the synchrotron radiation comes in. Yeah, so it has multiple components. I'll not get into the details of that. Just wanted to show you the experimental setup. And it's important to calibrate the data before you actually go on to analyze the data. And in this case, I used the argon data to calibrate. So as I said earlier, detector detects multiple electrons at the same time coming from the same ionization event. So the data is collected by the computer in the form of electrons or electrons and photons. So this E and 2E and 3E and 4E that you see here are electron coincidences. Yeah. So if you see, for example, EE, it means 2 electrons are detected from the experiment by the detector. If there are 3 electrons, you see these are 3 electrons that are detected simultaneously, and so forth. So these are the types of electron coincidences. Yeah. This is an example of what the data looks like. This is electron 1, this is electron 2, and this is the faster electron, this is a slower one. That's how these are arranged. So if the electron has a long time of flight, for example, then the detector detects it quite fast, meaning that the electron has a higher kinetic energy. If the electron has a low time of flight, for example, then the detector detects is very slow and it has a slower kinetic energy. So that's how it works. And when you plot these data onto a map, you require a certain amount of coding skills for that. So when you plot these electron data into a map, this is how it basically looks like. Yeah. So we have x-axis where we have the time of flight of fast electron, in this case, this row. And this axis is the time of flight of late electron, which is this row. Yeah. And here I'm showing you example of double electron coincidence, meaning that 2 electrons are detected at the same time. And this is how it basically looks. You can see there are certain repetitive structures here. Yeah. These are the bunches or cycles. So one ionization event, second ionization event, third ionization event. If you remember, while talking about synchrotron radiation, I talked about pulsed or pulsed radiation. This is what it is. When you zoom into it a little bit, you see something like this. Okay, so this is this small section of it, for example. Here the range is 0 to 1600 eV. Here the range is 60 to 100 eV. So if this is a whole cake, this is a small piece of the cake. Yeah. So what you're looking here are basically detected electrons, and it's quite fascinating to work with them. Yeah. The next job here is to identify what these features really are, and it's quite interesting to be able to understand and identify and assign these features. So to calibrate, for example, this data, what you need to do is you need to plot the data. Yeah, you need to look at the spectrum of the data. Here, if I plot one data file, it looks something like this. There's a small peak over here. Let's not get into the details of what it is. And if you plot a second set of data, you see very similar structure. If you plot the third data, you see something like this. These individual data are basically coming from different photon energies we used. So for example, if this is 250 eV, this is 251 eV, this is 252 eV, and so on. Okay, so different photon energies are used here. And when you come here in the third data, for example, you see there's something popping up at the corner. Yeah. When you move ahead, the same thing is shifted a little bit. When you move to higher photon energies, you see there's a shift in these features. Yeah, they are shifting. So this is happening because if you remember, I talked about Einstein's photoelectric effect, and there was this equation wherein the electron kinetic energy basically depends on photon energy. So when you change the photon energy, you change the kinetic energy of the photoelectrons emitted. So these shifted peaks that you see are photoelectron peaks. Okay, and these peaks which don't move or are at the same place, they are the Auger features or Auger electrons. Okay, because Auger electrons do not depend on the photon energies, and so we see them at the very same place. They don't move. And so that helps us basically to understand the underlying pattern here. Yeah. So here I have used the photon energy of 250 to 260 eV for these black spectrum. And here from 262 to 302 eV and a bunch more, all the way up to 1912 eV. I can't include all the examples here, but this is just to make you understand that we plot these data, we see the shift in the photoelectrons or photoelectron peaks, and then we basically identify the pattern, and then we plot or fit a function out of it. As I said, changing photon energy produces a predictable shift in kinetic energy and therefore also in the time of flight. And when you plot these shifts, basically you see a curve which looks something like this. Yeah. So one data point, one shift, second data point, second peak, third data point, third, and so on, all the way up to higher kinetic energies. So you see that there is a pattern that we see here with changing photon energies and changing kinetic energies of the electron. And we fit a function out of these data points, and we get the parameters, basically fitting parameters, which is then used to convert those time of flights into kinetic energies, because electrons are not detected in kinetic energies when the detector detects them. It measures them not in terms of kinetic energies, but in terms of time of flights or channels, say, which then need to be converted into kinetic energies using this calibration function. So it's very important to basically calibrate the data before you actually go on to analyze them or assign features to your data. Yeah. How much time do we have? We still have quite some time, right? Because I have a lot of things to talk about. Okay.
Yeah, we have quite a lot of time.
Okay. So let's continue then. So the analysis approach that that I have been using or I have used is something like this. So I will give an example of 1830 eV, which is the photon energy, and I will give an example here of 4 electron coincidence data. So it's E, 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 meaning that 4 electrons are detected at the same time. So what we do is we basically gate or filter out our data in this range, which is 145 to 165. Okay, and this basically denotes a specific electron, because different electrons have different kinetic energies depending on where they're coming from initially. Yeah. So photoelectrons have a different kinetic energy. Auger electrons have a different kinetic energy, and so forth. So when we initially ionize our atom, one electron gets kicked out. The atom is now in a singly ionized state, meaning that the atom is lacking one electron, right? So we call it, for example, in this case, we call it krypton plus. Here it means that the atom is lacking one electron. Yeah. And the energy range for this particular electron is 145 to 165 eV, electron volts. Yeah. So what we do is when we have this data with us, we gate or filter on one of the columns of electrons with this particular energy. Yeah. And then we move on or plot the second electron, and we see a certain spectrum. And then we gate on that particular second electron as well in terms of kinetic energies. So for example, in this case, if this was the initial state, one electron missing, this is the second stage where two electrons are missing. Yeah. So these are basically Auger states or primary Auger decay features that you see over here. In this case, this is from 2p minus 1 to 3d minus 2 state. Now here, two electrons are missing. This is 2p minus 1 to 3p minus 1 and 3d minus 1, meaning that one electron is missing from this orbital and second electron is missing from this orbital. Yeah. And in the third example, from 2p minus 1 to 3p minus 2, meaning that one electron is missing from, both the electrons are missing from 3p orbital. Yeah. And all of them have different kinetic energies. The electrons, which is coming from, say, 3d minus 2 final state, has a different kinetic energy. This state has a different kinetic energy, and this electron has a different kinetic energy. And so what we can do is when we code, we can basically filter on those kinetic energies to be able to see higher ionized states. In this case, since there are two electrons missing, this is krypton plus plus state. Yeah. And when we gate on those and we plot the third electron, we see even slower electrons in the range of, say, 0 to 100 or 120 EV. And these are the states where three electrons are missing, yeah, from here. And so we keep on continuing to all the way to the fourth electron, wherein we plot the data up to 0 to 60 electron volts, and we can then analyze the slowest of electrons. So the idea is to basically utilize or use the data in such a way that you can filter out certain kinetic energies which corresponds to certain processes, right? So for example, if you gate on this feature or this decay, this is one example of a decay. If you filter on this data, this decay only, then it will give you all the states which came from this decay. Yeah. If you gate on this feature, it will give you all the transitions or all the states which came from or which were initiated by this particular decay. And the same with all the rest. Yeah. So this is just an example of the analysis approach that we use in coincidence spectroscopy, wherein we have multi-electron coincidence data. We use different filters depending on the kinetic energies of the electrons, and then we project and see what the transitions or states really are. Okay, we can do the same thing also in terms of coincidence, meaning that we can plot the early electron and the late electron, and we can map out how the electrons correlate with one another. In this example, you can see that I have gated on 1400 to 1500 EV on the first E1 electron. Again, I'm giving the example of 4-electron coincidence. Yeah. So on the first electron, you basically filter out 1400 to 1500 EV. On the second electron, you filter out 145 to 165 EV. And then you plot the third and the fourth electron in coincidence. Here, I have plotted the third electron and the fourth electron on the y-axis. And this is what it looks like. Yeah. So the next stage is to identify what these features really are. I don't know. Yeah, that's what we need to identify what they are. And there's a second example here. Again, it is gated on a different Auger feature. And here it is gated on a different Auger feature, right? So what we do is, this is a different transition This is a different transition. This is a different transition. And when we filter those and plot the other columns, we can then see all the states or transitions which were initiated by these respective transitions. Okay. What are these features? I don't know. We need to find out, right? I will give you one example of how or what the features really are in one particular example. But before that, let me again repeat the convention or the notation that I have used. So if we basically create an initial hole in one of the shells, a second electron fills that hole, and a third electron gets kicked out. Yeah. So in this particular example, we call it L2, M3, M4, 5. L2 because there's a hole over here in the initial L2 shell. This is called L2 or 2p. You can call it whatever you want, but this is the nomenclature that is often used in Auger decay literature, for example. And M3 and M4, 5 are the orbitals that are involved in the later processes. In this case, this one and this one. Okay, so we call it L2, M3, M4, 5. Or you can also use this ionic notation wherein 2p minus 1 shows the initial state and 3p minus 1, 3d minus 1 shows the final state. Yeah. And we have a coincidence map. So the detector detected the electrons. We did the calibration and converted the time of flights into kinetic energies. And now what we have is we have two columns of data of electrons, and we plot them. The first electron in x-axis, the second electron in the y-axis. Yeah, depending on which one is faster and which one is slower. You can also do the opposite. And we see something interesting. We see an interesting plot. We don't know what these are. And so we need to check the literature to find out what these features really are. As you can see, the x-axis has a range of 600 to, I don't know, close to 1800 EV or so. Beyond that, you don't see any features. Yeah, here from 0 to 500 EV. I have kept quite some space over here so as to include all the features. These are the main features, these bright spots. But it's always good to include a wide range so that you don't miss out on any electronic features. What you're looking in the screens right now, in your screen right now, is basically electrons themselves. Well, not exactly electrons themselves, but these are the points wherein the electrons strike the detectors, and the detectors basically detect them. And that's the data that we're looking at right now. Yeah. So if you're wondering what this histogram on the right side and on the top side is, the histogram on the right side denotes the 2p photoelectrons. In this case, this peak and this peak represents photoelectrons. Photoelectrons are the ones that we initially ejected. Yeah, we used synchrotron radiation, we kicked out electrons. Those are our photoelectrons. Okay, and that's what we're looking at these spots. And this histogram basically shows the Auger spectrum, meaning these are the Auger electrons, these electrons. Okay, if you look at this energy level diagram, this electron is your photoelectron, which was emitted earlier, and this emitted electron is the Auger electron, okay, which gets emitted after the photoionization and after all this process happens. So what you see here in this spectrum is this electron, and what you see here in this spectrum is this electron, and you can clearly see that they are in correlation with each other. Yeah. So this is a very powerful technique by which you can basically correlate electrons together and understand the processes better. Now, so far, I have been able to identify these features. I will very quickly show you what they are, but you don't really have to understand all of it, of course. But nevertheless, I will mention. So this very bright and most prominent feature is L3, M4, 5, M4, 5. In order to understand what these terms really mean, again, you have to look at the energy level diagram. If you give enough time to yourself, you can identify where the initial hole was and what were the two shells involved later on in order to complete the process. Yeah. So initial hole in L3 shell, a second electron from M4, 5 shell fills that hole, and a third electron gets kicked out. So it's a three-step process, as I explained earlier, okay? And this is the electron that gets ejected from this feature, okay? Similarly, there are multiple other features coming from the same initial photoionization of L3 electron, okay, or an electron in the L3 shell. Similarly, we have other features from L2 shell. There are some additional features which have very low kinetic energies here, as you can see, in the range of 0 to 60 eV. These are the M and N features, okay? And some more features over here, yeah? So even though you don't understand what they all really mean, in a nutshell, what they are basically the transitions, the states, the electrons that we see after these respective Auger decay processes. Okay, so these are all Auger electrons, and these are photoelectrons. So here, these indicate 2p photoelectrons. Here, these are the Auger features that came from ionizing electrons from L2 shell, and these are the Auger electrons that came from ionizing the L3 shell. These are different shells of an atom, okay? So you ionize this electron, you see these features. You ionize this electron, you see these features. And what you do then is you compare it with the literature. This is not my data. This is an already published data where you can see that at these energies, these are the Auger features, yeah? L3, M1, M45, L3, M45, M23, whatever, doesn't matter, right? So we see different states or different transitions at different energies, and we compare them with our data, and we see if it matches or not, yeah? So if it is matching, well and fine. If it doesn't match, we check our calibration again, we recalibrate, and we analyze again, okay? So as you can see, it is quite a good match that we see here with our experimental data and the literature data. Unfortunately, for krypton, there's not much literature available out there, especially not for what I'm studying. But nevertheless, we can check it roughly if it matches or not. So when you first eject an electron, there can be multiple ways by which it can de-excite. So we hit the 2p shell, we eject an electron. What happens after that? We don't know. The atom can basically de-excite itself by going through multiple Auger decay or Auger channels. And that's what the target basically is, to be able to understand what are the pathways that the atom uses to de-excite itself or to come to the ground state. Yeah, that's the main goal. So in this case, for example, the atom decays by two channels. If you excite or ionize the electron from this shell, you can see that it decays into two whole final states via normal Auger decay. And if you ionize electrons from this shell, it mostly decays directly, but about 10% follow the Koster-Kronig cascade, meaning that CK transition means when two orbitals involved are the same. So if the transition is happening between L1 and L2, that's the CK transition. If the transition is happening between M2 and M3, that's the CK transition, yeah? So if the shells are the same, then that's CK transition. And in this case also, about 10% of them follow the CK transition. So I've mentioned the same thing over here in terms of a small flowchart. So L3mm and L2mm, basically these are the Auger decays that happens normally, that decays normally. And there's a cascade decay wherein there's an intermediate state over here, yeah, which then leads to a final state of MMN, okay? So these are basically nothing but decay pathways. Okay, there's then, as I mentioned, the same a question of what happens after that. Okay, we photoionize, we see the Auger decay. What after that? Is the atom already in ground state? Yes, no. It could be, it could not be. Because if the atom is already in ground state, well and fine. If that atom is not completely de-excited, then it again undergoes another Auger transition, meaning that all those LMM features that we saw earlier, they trigger another cascade or another channel, basically. Okay. And in this case, for example, these are these red diagrams that there's these red curves that you see are the theoretical results for this photon energy for the same krypton. And these black curves that you see are L23 mm Auger spectrum. And here are the photon energies, sorry, the kinetic energies of these electrons. You can see these are basically the same diagram that I showed you earlier. These and these, they're all the same, so don't get confused. Yeah. But here, one interesting thing I wanted to show you, and that is this middle spectrum, which follows a slightly different pathway than the normal Auger decay. As I said earlier, this one is populated by the CK transition or caustic-chronic transition that I said. Okay, this is the normal Auger decay, this is the CK transition. And these red and blue bars that you see basically indicate the intensities of these states. Yeah. So do we have time? If we have time, then I would like to show you maybe one example. I'll skip this part because it's a bit too much. Yeah. So I will show you one example of how an atom is initially ionized and how the electrons or states are detected. So here I have mentioned one example of xenon. Yeah. I'll go step by step so that it's easier to follow. So we use synchrotron radiation or X radiation, hard X radiation, to ionize the initial electron or initial cell. Yeah, the electron is located in 3D shell, so we remove that electron. So the atom is lacking one electron now. Yeah, there are multiple ways by which the atom can de-excite itself, meaning that it can either go to this state, meaning that the electrons that are now involved, the shells that are now involved are 4D shells, and 2 electrons can get missing from here in order to stabilize this hole. Yeah, or there can be electrons from 4p or 4D shells, and it can go to this state, or this state, or this state, or this state, and so on. So there are multiple ways by which the transitions can happen in order to stabilize the atom, because our atom is unstable right now. In this case, the xenon atom is unstable right now because we have created a hole over here. We have removed one electron here. Yeah. So in order to fill that hole, the atom can go to multiple final states. And there are different probabilities for that to happen. 46% chance that it decays by this method or by this state, 28% chance by this, 12%, and so on. But still, our atom is not completely stable. Why? Because there are 2 holes here, right? 2 electrons missing in this level. The involved shells are different, but the number of electrons involved is the same. Yeah, -2, minus 1 is -2, all of them -2. So 2 electrons are missing. The atom is not yet stable. And again, so it goes further, it decays further, creating a triply ionized state, meaning that there are again 3 electrons missing. Yeah, in this case, -1, -2. And these are the different shells of atoms that are involved. And these are the final states. Yeah. So as you can see, first step, second step, third step. These 2 states come from this step only. These 2 steps come from this step and this step, right? So it's actually a complete network of how an atom initially ionized tries to stabilize itself by releasing electrons. Yeah, and the involved electrons might come from different shells and might lead to different final states. And that's what coincidence spectroscopy makes it very easy. Okay, and that's what we primarily do. Here I try to give you one example of xenon. This is xenon plus. This is xenon plus plus, meaning 2 electrons missing. This is xenon plus plus plus, meaning 3 electrons missing, and so forth. So using coincidence spectroscopy, it's very much possible to be able to identify the decay pathway of an excited atom or atomic system, if that makes sense. Okay. I would love to talk about the coincidence stacking method that we use, but maybe that'll be a bit too much. Okay. So what I intend to do in the future is identify the secondary Auger decay, not the primary one. I already showed you the primary one. What I want to do is identify the transition that happens afterwards. And that's the M and N Auger channel in this case, and satellite states basically at much higher resolution and spectral precision. And satellite states are basically those states which we see when for example, we eject an electron out of an atom, and the rest of the electrons basically don't see the atom the same way. Meaning that when there's one electron missing, the rest of the electrons are not in the same potential. Yeah. So they kind of try to eject themselves out or go to a higher excited state. And those states are called satellite states. And I also intend to investigate into Auger pathways of resonantly excited data, meaning by resonant excitation, I mean that your photon energy is very close to the binding energy of that particular shell. And when you do that, you again see some exciting features. We call it resonance excitation. And then also compare monomers and clusters to understand how the cluster sizes basically affect the electronic structure. And we can already clearly see the differences in terms of electron kinetic energies. Again, there are multiple dynamics involved here, right? Because atoms don't behave the same way when they are isolated and when they are in clusters. So that's something that I want to investigate. And also something called PCI effects, or post-collision interaction. To put it in simple terms, what it means is you remove one, let's say, photoelectron from an atom, yeah, and Auger decay follows. So you have photoelectron getting released and you have Auger electrons getting released. And both of them have different kinetic energies when they get released. They have different energies. Auger electrons in this particular case are very fast, in the regime of, say, 1100 to 1500 eV or so. So they're pretty fast. Whereas photoelectrons are very slow. Yeah. So if there's, let's say, a very slow photoelectron moving out of an atom, and there's very fast Auger electrons coming out, it's basically the interaction, the apparent interaction that happens between these two electrons. And that again brings some interesting results or some interesting effects that we can see. These are called the PCI effects. Let me summarize today's talk. We talked a little bit about how synchrotron radiation works and how X-ray free electron lasers work and what my experimental setup was. We talked about how photon energies, how basically these data are calibrated and how photoelectron peaks move or shift with changing photon energies, but Auger electrons don't move. And so we can basically track and fit a function with those moving photon energy peaks from the spectrum. I talked a little bit about, or at least tried to talk a little bit about the analysis approach that we use in our group in order to, for instance, analyze the electron coincidence data. In this case, I gave you an example of 4-electron coincidence. We looked at a coincidence map wherein we have a faster electron plotted on the x-axis and a slower electron plotted on the y-axis, and we can basically see and analyze the electron dynamics involved there, and we can identify and assign features for those electrons. And we looked at some spectrum that were basically, that came from different Auger pathways or different decay pathways. And this I didn't talk about because, again, that I thought would be a bit too much for today's talk. But anyway, I intended to, but maybe that'll be a bit too long for today's talk. Thank you very much for listening to me. And this is a group photograph of the AG Erasmus group in our university. All of these are very amazing guys. Everybody's working in different but related stuff. So we also basically work on something called ICD, or interatomic and intermolecular Coulombic decay, which is when after the initial photoionization, the atom basically transfers the energy to a nearby atom. Meaning, so if you have, let's say, one atom, second atom, yeah, very close to each other, this atom is excited, it releases an electron and transfers the energy to this atom, and a third electron gets kicked out from the second atom, not from this atom, but from this atom. Yeah, so it releases a very slow electron, and we call it an ICD electron. And that ICD electron is very interesting because it is believed that, and it is at least theoretically understood, that these ICD electrons are involved in radiation damage. Okay, meaning that these electrons can potentially break DNA strands, but it has not been proven yet. And our group is trying to prove this phenomena experimentally. So this is one of the things that we are trying to do, along with a bunch of other interesting stuff. So that would be it from my side. Thank you very much for listening to me. I hope it was fruitful, and I was able to explain to you a little bit of information about what coincidence is, and how synchrotrons work, and how we analyze the data. Thank you.
So thank you so much, sir, for such an insightful and inspiring session. We have also received several thoughtful questions from participants through our registration responses. So I would now like to move into the Q&A segment and present some of the questions. So, firstly, this has quite caught my eye, and this is that what are some technologies or software that you use that you think you should have discovered earlier, and some skills you recommend that are going to be a must in this field in upcoming years?
Okay, that's a very good question, actually. So the skills that I think I should have known earlier are maybe coding skills. I was not so good at programming, and it's quite evident that coding is a very important skill that you should know. Of course, in this day and age, it's quite easy to code with AI and LLMs and so forth, but in physics, it's very important that you know your code well, even though you can simply just tell the AI to do it. It's important to code yourself. That's one thing. And the programming language that we use quite extensively is Python to analyze the data, and we also use Fortran to do simulations. So these are a few things that I think I know now, but I think that I should have. It would have been better if I had known these skills before. And to answer the second part of the question, the skills I think that you need is, of course, you need to be curious. It's not exactly a skill, but curiosity is very important. And even in the field of physics, pretty much all of the fields of physics, even in theoretical physics, you need to be able to code, and you need to have a decent understanding of mathematics. So yeah, these are the skills that you need primarily.
Since you just mentioned about the AI, we have another questions related to AI, and it goes like, how can AI-driven computational models help scale these techniques to detect subtle anomalies linked to beyond standard model PSM physics?
Okay, so I think AI is quite extensively used even now. Or at least even in our group, we are trying to incorporate machine learning algorithms and neural networks, physics-informed neural networks in our analysis. But having said that, it's quite important to have the fundamental physics correct in the first place. it's important to have your, for example, calibration and systematic uncertainties, because there can be a lot of uncertainties in these kind of studies. So it's quite important to have those uncertainties quantified properly in order to be able to integrate machine learning models to them. I think I can give you one example wherein it is quite extensively used is gravitational wave astronomy. They use machine learning algorithms to basically identify and detect gravitational waves. They're also quite extensively used in Coltrane's experiments, for example. Even in particle physics, it's quite extensively used these days. And yeah, I mean, I think it's a very powerful tool, still under development, especially in areas of physics, but I think it has a lot of potential. Yeah, it can be used to identify noise, anomalies, and so forth.
It figures that we have another questions in our chat section, so I would now request you to kindly look through it and answer the query in the chat inbox.
Okay, yeah, I can see the question. It seems to be a different field in Germany. Is it because that field isn't available there, or are you planning to change your field during your PhD? No, you don't sound dumb. That's a very good question. Thank you very much for asking. Yes, you are right that I was quite interested in the fields of quantum gravity. It's a theory-heavy field, but and I also took advanced quantum mechanics class in the first semester, but I then fell in love with particle physics and radiation physics. So I kind of switched from theoretical physics to experimental physics. I'm currently working on experimental physics. But again, yeah, that's not the field that I've like completely left. I still like take a lot of interest in theories of quantum gravity, but yeah, my work primarily revolves around experimental physics now. And as far as PhD is concerned, I think I'll do my PhD in astrophysics, because these Auger effects, ICD phenomena, are also quite widely applicable in certain astrophysical processes as well, for example, in interstellar clouds and gases and so forth. So that's what my plan is so far, but let's see.
If anyone has any queries, you can kindly ask him. If not, then you can just move in. You can just raise your hand and ask your questions. Well, it seems that with your insightful lessons, everyone has their answers. So, before we conclude today's session, I would highly encourage everyone to explore Mr. Sunny Labh's Medium profile that I have provided in the chat sections. His articles are really engaging for anyone interested, and also it's a wonderful platform for staying connected with modern scientific discussions and learning beyond the classroom. As we come to the end of today's webinar, I would like to leave everyone with a simple thought. Science does not begin in laboratories, it begins with curiosity. Thank you so much for your time, and I hope that you will always be interested in science and learning more. Thank you. Thank you, sir.
Thank you very much.